Thank you. So I'll be talking about how to look like a statistician, a developer's guide to probabilistic programming. So first, something about me. I'm Evelina Gabasova. I work in the Alan Turing Institute, which is the British National Institute for Data Science and Artificial Intelligence. And I work there as a data scientist. So anyone who mentions data science in a talk is required by law to include this diagram. So data science is supposed to be on the boundary between computer science, mathematics, and statistics, and domain knowledge. Well, I like my definition that my boss uses a bit more, and he says that a data scientist is someone who's better at programming than a statistician, and better at statistics than a programmer. So we are sort of on the boundary between these two things, which means quite often we feel like that. So I have no idea what I'm doing. So why would you even want to look like a statistician, except when you are a data scientist? Well, this is a stereotypical image of a statistician. It's actually a famous statistician called Brian Cox. He developed survival models. So how to survive with statistics if you are only a developer? Well, the reason is that it's not just about statistics. This will be about probabilistic modeling. And a lot of machine learning is about probabilistic modeling. And this is sort of on a boundary between machine learning and statistics. So why should we care about probabilistic programming? Well, I'll be talking a bit about probabilistic models and how functional programming fits in with that. And if you went to the unconference talks yesterday, they mentioned some of this already, but I will approach it from a very different angle. So we can talk about mathematics, and it can be a very dry talk, and you can be sleeping within 45 minutes because you are after lunch. But I wanted to start with some specific example. So Stack Overflow does developer surveys where they ask developers to fill in a questionnaire with a lot of questions, and then they always publish some reports on that. So I used data from the developer survey in 2017 because there were some articles from that survey that made rounds around the internet. Like, developers who use spaces make more money than developers who use tabs. That's weird, right? Why is that? Well, if you want to know more about my analysis of that, go to my blog. I published a blog post on that. But the first thing that I did after I saw this, they actually published the data. So I decided, okay, let's have a look.
I read your article on this one, I think.
So this is a very catchy article, and even serious news outlets took it over. Programmers who use spaces are paid more. What does it mean if someone is paid more? Well, let's have a look at the actual data. So the first thing that any data scientist does is plot the data to see how they actually look like. So this is the salary distribution that was reported by developers in the survey. You can see that there is a huge bump around $50,000. And well, I looked at it and I thought, okay, this is weird, because there is a huge bump in the beginning. What's happening there? Let's look at it in a bit more detail. So I looked at countries where developers report their annual salary below $3,000. And that's $250 a month. That's not much. The first one is India. India is not a very rich country. I don't know that much about India, so maybe. But the second one is Poland. Poland is in Central Europe. I'm originally from Czech Republic, and I know that Poland is not some developing country. It's a normal country. And then Russia, a bit weird. But here, look, Germany. Germany is a very rich country. So how come there are developers who report their annual salary below $3,000? Well, you might have guessed what's happening there, but I looked at the actual salary distributions from different countries. These are the countries that looked normal, like India, France, UK. They have one nice big bump around some value. That's it. So that means that the developers are paid around that value. But this is how it looks in Central and Eastern Europe. You can see that the distributions look very different. See, these ones have one bump, these ones have two bumps, and one is here with a very low value, and the other one is shifted. So you can immediately see that, for example, in Germany, developers are paid more than in Poland, but both of these distributions have two bumps. So what's happening? It looks like one group of developers is paid like normal amount, and the other group of developers is paid nothing. Well, what's wrong? I looked at the actual questions that they were asking in the survey, and it said, what is your current annual underlying salary in local currency, blah, 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 blah. Well, who reads questions properly? So, my theory is that if I look at the salary distribution in Poland, that this small bump will be roughly 1/12 of the big bump. That's my theory. And let's test it with probabilistic programming, using probabilistic modeling. So my theory is that people don't read questions, and they just reported their annual salary. So later, I will tell you exactly how many people in Poland don't read questions properly. I love my Polish friends, so it's nothing against them. So I'll be using something called a mixture distribution. So what is a mixture distribution even? Well, these are like normal distributions, two Gaussians with different variances, different means. And I can use them as building blocks to create something called a mixture distribution, where I basically just sum the values of the two distributions. So this is one mixture distribution composed of the two Gaussians with equal weights. This is when I change the weights a bit. So now the first one has slightly smaller weight, the other one has a larger weight, so they change heights relatively compared to each other. And this is when I change the weights again. Now the first one has larger weight and the other one, etc. So this will allow me to balance between two distributions and find out how large proportion of the whole population is within the population that can't read questions, and how large proportion is in the population that can read questions. So how do I even come up with the actual numbers? Well, that's where probabilistic programming comes in. Now you might be sort of like, oh, distributions. If you hated your statistics classes, then you are probably feeling like that. Well, help is at hand. You probably don't need to know that much about it because there's probabilistic programming. So I, as a statistician, would formulate the model like this. And now there are a lot of Greek letters, and a lot of my friends just blank whenever they see anything Greek. So how do we even imagine these things properly? How do we work with them? Well, one very useful thing when you are dealing with probability distributions is sampling. And that's used for inference in a lot of probabilistic modeling. So I'll be talking a little about sampling. Does everyone know the Monty problem? Well, it's a famous problem with statistics that's very counterintuitive when you hear it for the first time. So the model comes from a US show, I believe, that's called Let's Make a Deal, where there were 3 doors, and the problem is formulated in a way that there is a car behind one of the doors, and people were competing to win the car. They usually came in crazy costumes, I'm not sure why. But they could win a nice Chevrolet. This was in the 70s, I believe. So the problem was that there was only one car behind one of the doors, and the other 2 doors had a goat. And you picked one of the doors, and then Monty Hall, the host, opened another door, and it showed a goat. And now you were tasked with the question, do you want to switch or not? Well, the most intuitive answer is it doesn't make any change if I switch because I picked a door. but we can actually see how it works out with the sampling. So yeah, just to demonstrate, let's pick one of the doors, and Monty Hall opens the door, and there is a goat. And should I switch or not? Well, I decided not to switch, and there is another goat. So I didn't win the car. So let's see how it actually looks in the code. F# is my language of choice, so all my demos today will be in F#. So we can basically formulate the game in our types. So door can hide either a goat or a car. Then a game is some sequence of doors, and I can either stay or switch. Let's generate some game. And now if I want to play a game, I will pick some initial door. Then the host will pick another door that doesn't contain a car. And then I decide to switch, so I pick a door, pick the other door, etc. And then based on my strategy, I pick the result. So the actual code is not that interesting. It's actually very procedural. So if I do 10 samples, if I play the game 10 times, what happens? If I decide to stay with my choice, I win a car in 30% of the cases. And if I decide to switch, I win a car in 90% of the times. Whoa. So this is very inaccurate, because I did just 10 samples. If I increase the number of samples to, let's say, 1,000, I will get a much better estimate. That should actually sum to 1, because these are probabilities. So if I decide to stay with 1,000 samples, I win in 33% of the cases. And if I decide to switch, then in 66% of the cases. This is much more realistic number, that actually if I sum these two, I'm closer to 1. So that's one very important feature of Monte Carlo sampling. The more samples I take, the closer I am to the actual probability I am trying to estimate. And this is a very simplistic example. In actual real-world examples, you need to take billions and billions of samples, and you may have gotten closer to the distribution that you are actually trying to estimate. Well, we are all functional programmers here, I believe, and this code is actually very ugly. And this is not really about probabilistic programming yet. So where does the probabilistic programming come into place? Well, I want to represent my distributions as something much more readable that I can look at and see what's happening there. So I decided to use one feature in F# which is called Computation Expressions. And you can define any non-standard computation using computation expressions. You can define monads using computation expressions, but you don't have to. You can do other things with them as well. So let's first look at the actual code, and then I will explain what's happening there. So right now, in F#, it's a statically typed language, and if I hover my mouse over something, it shows me a type of that thing that I'm hovering over. So this prob keyword defines my computation expression, and the magic happens inside the curly braces. So here I am defining a distribution, which is a uniform distribution across 3 doors. One contains a car, another contains a goat, and the third one contains a goat as well. And then I pick a door. So if I hover my mouse over this, this gives me a distribution. But if I look at the door, this gives me an actual door, a sample from that distribution. And if I decide to stay with my original choice, I'll just return that choice. And if I decide to switch, I switch to a different door. So here I am basically all the doors, well, the initial door, switch door, and the thing I'm returning, these are actual doors. But what's happening inside this computation expression is that I'm keeping track of all the probabilities, and I'm hiding them from the user. So So this is actually much more readable if you look at it. You can see what I'm doing there compared to the very procedural implementation of the sampling. So what's actually happening there? Well, the types are mostly the same. So door can be either a car or a goat. And then I have a value over which I'm iterating, and that's a door and its probability. And then a distribution is just sequence of these. So sequence of doors with their probability. And then I'm having just some helper functions to define a uniform distribution and a value with probability 1. And this is the computation expression that I was talking about. So you may find these familiar from monads, but this is not actually a proper monad because the types are slightly different. So my probabilistic computation can either return a value or it can take a sample which looks at the distribution, which are the doors and their probabilities, and a door that I picked, and then the other probabilistic computation that will come later on that. So what this does, it basically just saves my choices of doors and their probabilities so that I can do something with them later. Because in real-world probabilistic programming, there is a lot of magic happening behind the scenes. So this basically just saves what I'm doing and what are the distributions so that I can process them somehow a bit later. So this looks just like a pick from a distribution, but it's saving the distribution from which I am picking a door and passing it on to the next choice. So for example, here, the initial door comes from a different distribution than the switched door. And it's all happening behind the scenes so that the user doesn't have to see it. And that's basically the main point of probabilistic programming, because you want probability distributions to become first-class citizens in your language. And here, what I'm doing is I'm just looking at the actual values and multiplying probabilities. So in this case, the actual code is not that important. This is just about summing or multiplying the probabilities of the doors that I picked. And let's summarize the results and look at the overall results. So if I stay with my first choice, I win a car with 33% probability. If I decide to, and goat with 67%. And if I decide to switch, then I win a car with 67% probability and goat with 33%. What's actually happening inside? I added some prints to see what will happen. So if I decide to switch, this is actually what my computation expression is saving inside. Well, in the first round, I pick a car with probability 33%. And if I decide to switch, then I certainly get a goat with probability 1. And in the first case, if I pick a goat and I decide to switch, then I win a car with probability 1. And if I picked a goat, the other goat with 33% probability, then I win a car as well. And that's what my computation expression saved inside, basically. All my picks and their probabilities. And if I wanted, I could do something much more clever inside, like normalize the probabilities or do some clever inference. So, what can we do with our mixture distribution here? As I said, this is quite ugly and a lot of Greek letters, so let's rewrite it in English. So, my theory is that the developer's salary in the Stack Overflow survey is that it's equal to the probability that someone answered the question correctly times their actual annual salary plus the probability that they made a mistake, which is 1 minus the probability that they were correct, times 1/12 of the annual salary. So what can we do with this now? Well, we can do basically exactly the same thing. Now, it's very easy to actually compute the salary if we knew all the unknown parameters. That means the probability that someone is correct and the actual value of the annual salary. And that's a very good feature in a probabilistic model, because it makes all the inference relatively easy. So what I want to write in probabilistic programming, as I said, I want to make the probability distributions first-class citizens in my language. So what I want to write is basically say that salary is a Gaussian with some mean and some variance. And probability of a mistake is Bernoulli. That's just a coin toss, basically. Probability between 0 and 1 that someone is correct or that a coin is rigged. It just has a fancy name because of statistics. And my observed value, if there is a mistake, then it's 1/12 of the salary. Otherwise, it's the actual salary value. This is what I want to write, because this is readable to anyone. I don't want to care how the parameters are actually inferred. I don't want to care about what the distributions are doing behind. I want to give it the data and then just operate with it within my programming language. So let's look at how can we formulate this with with computation expressions again. So here with the Monty Hall problem, this was fairly readable. I was just picking doors. So how does it look for a mixture of Gaussians? Well, first of all, my types, they look basically almost the same as they looked in the Monty Hall problem. Here I have two distributions right now. I have a Gaussian and the Bernoulli. Gaussian takes two parameters, mean and a variance. Bernoulli takes just one probability. And I have my probabilistic computation, which is exactly the same as I had in the Monty Hall problem. If I look at it, here you see. This is exactly the same thing. So, how will my program look now? My model, again, be wrapped in the computation expression that I defined here. And I can say that the yearly salary is a Gaussian with some prior values. And the probability of a mistake is basically just like 0.5, 50% of mistake or not. And if the mistake is true, then return the yearly salary divided by 12, otherwise return the actual salary. So you can see this is very close to the pseudocode I had in my slide, and it's readable. And if I look at the distributions, this is a probability distribution. This is a Gaussian. But the value that I picked from it has type value, which I have here, and it's a just wrapper around float. So now I can work with it as a normal number. It's not a distribution anymore in the probabilistic computation. And a mistake is also just a float, just a value. So I can do things like divide them, which normally doing that with a distribution is non-straightforward. So this pretends to be just a value. But behind the scenes, again, it's keeping track of all these probabilities, and I can do something clever with them later on. Because in realistic probabilistic computations, you do things like differentiate the program with respect to variables, which is very complex, very cool. So you want to keep track of what the computation is doing so that you can use it later. So what did I do here? Well, how do I actually infer the mean and the variance and the probability that someone made a mistake? This is highly non-straightforward. Well, in this case, it would be relatively simple, because it's a simple model. But once we go to much more realistic models, this is highly non-straightforward. For example, these are screenshots from my PhD thesis, because you literally get a PhD for this kind of stuff. So this is just to scare you. I don't remember what that means either anymore. But this is just to demonstrate that you literally get a PhD for defining inference rules for parameters in a probabilistic model. And not from some dodgy university. So here, in this case, I decided to do just a very simple thing that I hope I will explain to you, but it will be the slowest probability inference engine ever. But, again, the important thing is that this happens behind the scenes. So you, as a user, you don't have to care, and it's up to me to optimize this. And you don't need to do all these things. So my algorithm that I decided to use is called complete enumeration. And if you want to read more about it, you will find it in any machine learning textbook in the chapter of how not to do it. Because this is highly inefficient. So this is my distribution that I'm trying to fit. And what I will do, I will basically use my two Gaussians and try to give them all the different values within a reasonable range. So I will try to vary the weights that shift the proportions between the two Gaussians. I will try to vary their positions, that means the position of their means, and see which one fits the best, basically. So, and to make it even simpler, because my distribution was basically discrete, I had just the observations. And this is a histogram where the height of the bin shows how many observations fall into that bin. So I will do the same with my various probabilistic distributions, that I change the parameters and I will discretize them as well. And I will get nice bins again. And then I can just compare how many people would fall into each bin under my theoretical distribution and how many people fall into that bin in the actual survey, and find the distribution that fits the best. And this should work. So let's see how my inference engine actually works. So I will bin it by $1,000. Okay, oh, I should actually evaluate all the things I had in the beginning. So this is the code that actually varies the distributions. So if it's a Gaussian, then I look at plus and minus 3 standard deviations, which is where 99% of the data should be. And then just step through that and try all the different values. And for Bernoulli, I will just basically iterate through all the different probabilities with a step of 5%. So this is it. This is my discretization function that just rounds things into bins. And now this code actually looks at what I got from my probabilistic computation, which is the model. And if I had a sample of a distribution and some further probabilistic computation, then I vary the parameters of the distributions and then enumerate again all the possible choices and find out the probabilities. Let's see. And now here I compute the histograms where I varied all the values, I believe. And this is my function to compute like a similarity function between a distribution and a histogram that I observed. So let's run it. This will take a bit of time, so let's turn the timing on. Oh, this is actually still a function, sorry. And let's load the data. It's a lot of work. If you have never seen F#, then I'm actually using something really nice here, which is called type providers. So what I'm doing here is I'm just loading a file. Well, I'm just giving it a CSV file with the public results of the survey. And then I'm defining a CSV type provider based on that data. And what it does, it looks into the file, looks at first 100 rows, I think, and infers types of elements in that CSV table. And now I can actually access the data in there by doing, let's say, row dot. Come on. And you can see these were all the possible columns that were in that table, and there is a lot of it. But I'm interested in the country that people came from. And my type inference also tells me that country is a string, so I can just operate with this without actually looking into the table to see how the actual values in the table look. This is all happening in the type system. So let's load the data. It just makes all working with CSV files and other structured files very easy. So let's see how many data points we have. We have only 317 developers that come from Poland and did report a salary. All right, that's not too much. Let's run our slowest inference engine ever. And this is actually fairly quick. All right, so our most likely distribution is that the mean salary in Poland is $28,400 a year, with huge variance because we are dealing with huge numbers, and the Bernoulli probability of 25%, which means that 25% of developers in Poland can't read questions properly. Or they are probably just too busy working, so they don't read questions properly. So we have it quantified. Well, joke's on me, I'm from Czech Republic, and we are actually very similar cultures, so Czech developers probably can't read either. So we have the actual numbers, which is great, and when I plot it, it looks like this. So there is one bump of developers who don't read properly, and the other bump who can actually read properly. That's nice. I can quantify all this, and this all with probabilistic programming, and I can just write it in a very readable form that a non-statistician can read, or statistician can read and be impressed. All right, so how does probabilistic programming actually look in the real world? This was just my basically toy implementation. You don't want to be using this on any real world big data. In the real world, for example, there is a functional probabilistic programming language called Anglican in Clojure, and it uses some very similar mechanisms that I was using here. Basically use some kind of monadic structure to keep track of the probabilistic computation so that you can do clever things with it behind the scenes. Unfortunately, the most popular probabilistic programming languages are things like Stan, where you define the model like this, which is actually very similar to what I was defining it. But you can't actually use it within your programming language. You have to write it up separately and then compile it in C++ and then use that from a programming language. But language like Anglican is actually pretty usable, and it works on real world and large data as well. So my main goal in this was to just show you what are the principles of functional probabilistic programming, so that if you ever want to look like a statistician, you don't fall into Stan and use something proper. So when I was Googling how to look like a statistician, it gave me this image of a guy. So I hope we all feel like this guy. Maybe the opposite. Because, first of all, he's wearing a lab coat, which no statistician wears, and he's writing on the glass the other way around. So I hope you don't feel like this right now after this talk. And if you have any questions, just ping me on Twitter or find me around here. And I hope you got at least some idea how to do probabilistic programming in a functional programming language. And I think this is a very good framework to actually work with probabilistic models, because you can literally make them first-class citizens in a programming language. Thank you.